Audio basics. So the very most basic thing about audio is what's called a transducer. Now, a transducer is any device that converts one form of energy to another. Acoustic energy to electrical energy is a transducer. Acoustic energy is air motion, the molecules moving in the air that I'm speaking right now. Converted into electrical energy, that's a transducer, similar to what a microphone would do. Acoustic to mechanical energy, where the sound waves actually hit a diaphragm and it physically moves the diaphragm slightly. Like if I was to hold up a piece of paper and speak into it, it would move a little bit with the energy that I'm putting out into the air. Electrical to acoustical, your speakers take electricity in, make something move, create an air disturbance, you get acoustic energy. So everything is energy in one form or another. And the things that convert from one form to the next is called a transducer. Now, on a more basic level, everyone knows that you put gas into your car, the chemical energy gets changed into heat energy and motion, kinetic energy when you drive your car. Your car is a transducer. Your human body is a transducer. You eat food, chemical energy gets turned into heat energy and motion energy, kinetic energy. Your body's a transducer. A light bulb takes electricity and changes it into light energy. That's a transducer. So you see, it's a very basic concept of changing one energy form to another, but it's really, really important in recording arts because everything gets transduced and then retransduced. For example, when I record something, the acoustic energy of the molecules of the air moving because I've created a disturbance with my vocal cords, which actually comes from muscles moving, kinetic energy, which came from chemical energy in the first place because I ate my breakfast. So basically, all of this stuff is happening all around us at all times. Then it goes into a microphone, gets turned from acoustic energy, that gets changed into electrical energy, that goes into your computer, gets changed into digital numbers. That's not a transducer. It's all electrical. And then it goes from there, you manipulate it, you send it back out, goes to an amplifier, gets louder, and then the electricity goes into a speaker through magnetism, moves the diaphragm into kinetic energy, and moves the air again. You see, it's this big path, but it comes back to the same thing, that the air energy motion that I'm moving right now. You can store the energy, you can play it back at a new time. You can manipulate it. That's the value of what transducers do. It's almost like taking one kind of energy, changing it into another form that you can actually manipulate and do things with easier, and then bringing it back to the first form of energy that you started with. And that's really kind of a critical kind of a concept, because when I'm speaking now, the air is moving, it's hitting your ears, you're hearing it, but it's gone after I say it. It'll never come back. It's gone. I can say the same words, but it won't be the same. If you can save it, store it, manipulate it, and bring it back, that's what recording arts is. If you're a photographer, it's the same process, except now you're storing light energy and bringing it back for a later time of viewing. It's like looking back in time, just like when you go and you look at old pictures. You go, oh yeah, I remember that. That was 2 years ago. We were surfing or whatever. That's going back in time and looking at the energy that's been stored at that moment in a visual sense. Audio is the same way. Transducer, that's a big concept. That's an important concept because it's used in every part of what we do in recording arts. Let's talk about the basic sound wave. As I was talking to you, I'm creating a sound wave. You see on this drawing, you see sort of a cyclical kind of a sine wave, kind of a representation of a sound wave. But in reality, sound waves don't do like a water wave going vertical and up and down. You know, you splash a wave, it has ripples. Sound waves are longitudinal waves. You can see from the drawing above, what it is where air molecules get compressed and then rarefied, meaning less of them, and spots where there's more density of air molecules. So it sort of moves through the air, sort of like a spring moving in the air like that, as it vibrates through. So it's a longitudinal wave, not a vertical wave. That's how air gets kinetic energy and sound waves travel in the air. Wavelength. The wavelength, and this is a dead giveaway, it says wave length. It's the length that it takes for this wave to complete one cycle and come back to the same spot. So it's a length, measured in meters or feet, but it's a length. Amplitude is the maximum value of the wave, meaning how compressed the airwaves get. It's almost like volume up and down, except it's longitudinal. So it's the absolute maximum energy that the wave carries. The speed, because it has to travel with a speed. We know the speed of light is 10 to the 9th meters per second. Pretty fast, right? Sound is substantially slower. Sound is 1,130 feet per second, or 344 meters per second. Think about this. 1,130 feet is roughly, what is that? What's a football field length? Is 100 yards? So that's 300 something feet. So it's like 3 football fields. If I was 3 football fields away from you and I was screaming, you'd hear me a second later. I don't know, when I was a kid and we had a lot of thunderstorms, and we used to love to do this. We'd sit outside, we'd see lightning, and then we'd count 1 second, 2 seconds, and then by the time we heard the thunder crack, we could say, okay, if we consider the light traveling so fast that it's almost instantaneous, then we count, and then we could find out how far away the storm was, right? So if it was 3 seconds away, then it'd be like 3 times 1,130 feet away. So the speed of sound is at a specific air pressure, because obviously if there's less air molecules because you're up in the mountains, it's going to be a little different than if you're at sea level, because the medium that you're traveling, the sound's traveling in, is different, and specific temperatures too. Because when it's hotter out, the air molecules themselves have more energy and moving around in the air, because they're always sort of moving around. And in the cold, the air molecules are moving less, have less energy. But we're going to sort of not get into all that detail. We're just going to sort of assume that the speed of sound is always going to be considered at sea level and at about 59 degrees Fahrenheit. You know, sort of like an average kind of thing is going to be about 1,130 feet per second. Important to know the amplitude and the wave length of the wave as it comes back to the same spot in the periodic motion. So the speed of sound depends on the medium, the temperature, and the air humidity. Here's an example of different speeds. So air, 1,130 feet per second. But in water, sound travels a lot faster. Underwater, and you're making sound, it'll travel at 4,860 feet per second. Much, much faster, probably 4 times or so faster than in air. In concrete, it travels even faster. And in glass, it travels even faster, because it's more dense molecules and the energy vibrates through it faster.